Okay, we're going to start going over some of the problems here that are going to be due in chapter 2. And I want you guys to really get a good feel for how these problems work. Some of these are very easily adaptable into the system. I'm working on some of the others, but we'll go with working some of these. And if we need more, we'll go from there. All right, so let's take a look here at number 3. We're going to compute the binding energy for an alpha particle. Now, what do we know about the alpha particle? The alpha particle, we know, is going to have 4.00151 as its weight. What do we know that is in an alpha particle? Well, this is going to be a helium nucleus, so no electrons. But we know we have 4 nucleons, 2 of which are going to be protons. So we have 2 protons, which is going to be 1.00727 times 2. We have 2 neutrons, which is going to be 1.00866 times 2. Adding those up. And the way I am going to do this, I'm going to stop that there for just a minute, call up yield calculator. Up 1.00727 plus 1.00866 times 2. So 4.03186 here. All right. So what do we end up with over here? We've got the sum of its parts, which I can't do anything right. Let's try this. Six. That's 4.00151. Right. Minus, yeah, I got too many windows going on here. Let's see. 4.00151, right? Is that what I had said? Yeah. So we've got 0.03035. Okay. Turn here. Right, because I don't have this activated. There we go. Okay. So this is how many AMUs we have. Now, in order to be able to take the number of AMUs, translate that into MeV, which is what we're really looking for, I'm going to use 931.481 MeV per speed of light squared. Let's see what we come up with. So times 31.481, 28.27. And the answer here is 28.3. Now, for part B, we're going to be computing the average binding energy per nucleon. So if we take 28.3 MeV and divide it by, you guessed it, 4 nucleons, what we got. So we get 7.06 or 7.1 MeV, and that should agree with the book. All right. The last part of this is determine whether energy would be required or released if an alpha particle were produced by the fusion of two deuterons. In other words, you take these two and you throw them together. Compute the energy released or required and express your answer in units of MeV. So let's take, let's sort of clean the board up here a little bit. So we've got deuterons up here and we've got the alpha particles. So I think I'm just going to use that particular space. So we take two deuterons, which is these suckers, we smash them together. We're basically taking 2 times 2.01355. And the result out of that becomes 2.01355. 4.0271. Let's say there's a 0 there. Yeah. Okay. Now, compare that with the end product that we result in. The end product is going to be this. So we're going to have 4.00151. So we're going to go from this into this, which means we're going to end up having excess energy. The question is how much? So 0.02559. So again, we're going to turn around and we're going to take this, multiply it by 931, 481 MeV over C squared. And what do we end up with? Let's find out. .8. That's how much is released. That matches what we've had there. So very good. All right. Let's take a look here at number 5. The activity of the source is 298 becquerel. Estimate its activity in units of nanocuries. So starting off here, have 298 becquerel. Now we want to convert that into nanocuries. Now the question becomes exactly what's the relationship here between a becquerel and a nanocurie, or for that matter, just curies in general? Well, as it turns out, Google is a wonderful thing. If you ever forget anything like that, you can type it in. So 1 becquerel is this number of curies. I'm going to use a truncated version, 2.702. Well, I should have waited. Let's see. 2.702 7 times 10 to the minus 11th. Now, tell you what, I'm just going to try this all again because we want to be able to read what I'm typing here. So, curies over 1 becquerel. Now, we need to get the answer in nanocuries. So I know that 1 curie is going to be the same as, let's see, I believe a nanocurie is going to be times 10 to the 9th. So we should end up with 10 to the 9th. Nanocuries. So those cancel, these cancel. Now let's multiply this out. Let's see if I'm anywhere near close to being right. Let's see. Okay. Okay. Let's see what we get here. Now, I know 10 to the 11th and 10 to the 9th. Those two, if you multiply those together, end up being 10 to the minus 2. So basically, if I end up taking this result and dividing by 100, which is essentially going to be the same thing, it's 8.05. Is 8.05 the same thing as what I have here? Yep, 8.05 nanocuries. So let's take a look here at number 6. We're going to work the opposite direction. We're going to convert 15 millicuries to mega becquerel. So we can type all of that in here if we wished. I'm going to just go the hard way, convert becquerel. And you can see the difference here. 1 curie is equal to this number of becquerel. Let's try this whole thing. So how many millicurie do we have in 1 curie? Well, we should have 1,000. We cut something into 1,000 pieces. That's what milli stands for. So this should be what we end up with. Now, we found out here that 1 curie is going to be the same as 3.7 times 10 to the 10th becquerel. I believe that's what we found out. Let's try this. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, that's what we found out. All right. So we now are going to, by dimensional analysis, have gone from millicurie and from curie to becquerel. But how many, if we have 1 becquerel, how many mega becquerel do we have in that? So looks like we're going to be needing to rewrite that a little bit. So 1 mega becquerel should be 1 million becquerel. So now the becquerel cancel. So we've got, let's see, 10 says 10 to the first power, second, third, fourth, fifth, sixth. So we should end up, and then we've got, let's see, 10 times 10 is 100. 10 to the third is 1,000. 10 to the sixth is 1 million. Okay, so that's 10 to the sixth. 1,000 here is going to be 10 to the third. So putting all of this together, I'm going to end up with 15 times 3.7 times 10 to the 10th over 10 to the 9th. This cancels with most of this, leaving only that. So I should end up with 15 multiplied by 3.7, then multiplied by 10. Come up with 555. What's this thing was 555 megabecquerel. So don't forget to, oops. I'm not going to forget the unit here. It's 555 megabecquerel. Okay, not too bad so far. Okay, let's take a look at here in number 7. And I'll upload a video for more problems after this one is completed. So we'll go from there. Now, calculate how much the activity of cobalt-60 decreases in 1 month. And let's take the answer in a percentage. The half-life of cobalt-60 is 5.25 years. So we're looking for how much the activity decreases in 1 month. So we know that the half-life is 5.25 years. The problem is, it doesn't really tell us what's going on in terms of the number of months. So if I take this and multiply it by 1 year is equal to 12 months, essentially it's multiplying it by 1 because those are the same values. We end up with 63 months. Why is that important? Why is it relevant? Now, here is why it's relevant. What we're going to do is we're going to determine our decay constant. We know that one of our equations here, 0.693 divided by the half-life, will give us this value. 63 months. That turns out to be 0.011 per month. Now we can take this and I can give you an example as to what to do here. We've got the activity in the following month, whatever that happens to be, is the activity in the original month times E raised to the minus lambda t. Now, as it turns out, I'm going to say the month before has an activity of 1, and we don't know what this activity is, but we know that 1 month has passed, and we also know what the decay constant is. This gives us e to the minus 0.011. As it turns out, when you multiply that out on the calculator, come up with the activity is 0.989. So originally we had 100%, which I'm going to write as a decimal, just 1. And the following month, we have this as our activity. If you do the subtraction, you turn out this is the percent. This is the amount of difference. If you write that as a percentage, that means bumping the decimal point over a couple of spots. That means that the activity decreased by 1.1%. Okay. All right. I'm going to have more problems worked out in a subsequent video.